The index of refraction of nano-thickness metal layers varies with thickness, adjacent materials, and process. Procedures have been developed to cope with this in ways that had not been previously available. The typical deposition of a metal layer on a nanoscale looks like falling rain, produces little islands, and they get bigger with the nucleation of additional material, and they start to touch each other and coalesce or percolate as they get bigger and bigger till they finally form a continuous film. This slide illustrates in the lower left that the wavelength scale is orders of magnitude bigger than the scale of these nano islands. And so it behaves as a continuous sort of film when viewed from the point of view of a wavelength, which is much larger. Now, one thing to keep in mind is if we're controlling the thickness of our deposition with a quartz crystal monitor, it's seeing the collective mass that's deposited on it, but these are growing as islands. So what the crystal reads will be much thinner than the actual island height when they're separated by some distance because of its averaging effect. So in this case, with the big distance between islands, we'll see an order of magnitude lower thickness reading on the crystal monitor until the film starts to grow enough to have the islands touch or percolate or coalesce. And even in this case, with this simulation, we see that the thickness reading on the crystal is only approximately half of the actual height of the islands. Now here's the N values of a silver film deposited on fused silica with air as the final medium. And thin films like 2.4 nanometers here being the thinnest one shown out of these, and it shows all the way up to thicknesses of 50 nanometers. So somewhere past 20, going on 30 nanometers, this will look like a continuous film and have bulk properties, so it doesn't change thereafter as a function of the thickness of the coating. But in these nano-thickness layers, we'll start out with a sort of a resonance here in about the 400 to 500 nanometer range. And once we get up about 10 nanometers, we start to see this coalescence, and the indices start to approach the bulk values. This is the N values, and the K values for that same film look like this. And we can see again that the values look very metallic when we get up over about 30 nanometers. And there's very little change as a function of additional thickness. Here is a plot of the index versus thickness for that same film, the N value index. And we see that depending on the wavelength, they have slightly different characteristics, of course, but this one peaks up at about 11 nanometers. But also we see that it goes down to a bulk value, which in this case the N value is quite low at about 30 nanometers, and thereafter thickness doesn't matter. Here's the same kind of a plot for a different silver process where the fused silica substrate has about 7 nanometers of aluminum oxide, and then the thickness of silver, and then another 7 nanometers on top of that. So this process and adjacent layers varies with what we have here. And we'll see that in this case, 20 nanometers is where it starts to become bulk. There are other things in the literature where they show processes and adjacent layers where it will become as though it were a continuous bulk film at even thinner films, which is sometimes desirable. Here's the K value versus thickness for the silver on fused silicon air, and the K value on the aluminum oxide, silver aluminum oxide. Almost a decade ago, Stenzel and Macleod published an interesting work where at that time their basic approach was to characterize films at different thicknesses, but when they're using that in a design, they only use those films of thicknesses which have been characterized. So if they had characterized 10 nanometers thick and 20 nanometers thick and 30 nanometers thick, they would only design with those thicknesses and vary the other layers that were not that material. So that if they really would benefit by a 15 nanometer layer, it was not something they could use in their design. But what we've done here recently is to overcome that limitation so you can design fairly reliably with any thickness you want from the minimum that you've characterized up to the maximum, where you interpolate between the ones that you have actually produced to get a good estimation of what you would produce at some intermediate thickness. Here's chromium variation with thickness and wavelength, and the bulk values in black, and the thinner values are in colors here. So for example, if I'm in a design process and the design seems to want to benefit, we'll say, by a 6 nanometer thickness, the newer software will allow us to interpolate between 3 and 9 and get 6 or any other thickness in between 3 and 9, or in another case between 1.5 and 3, etc. Here is the K values for that same chrome film. So we interpolate in both N and K. Here's some interpolated values of different thicknesses, and here's some interpolated K values. Now I can design a black mirror which does not transmit and does not reflect more than 0.5% here. And so this happens to be an opaque film of chromium and then a dielectric metal, dielectric metal, dielectric of SiO2 and chrome. And if I can adjust the thicknesses of those layers on top of the opaque chrome, I can make a black design like this. However, if I were to assume that all of the chromium had the same N and K values, and I get a design like this, when I actually try to produce it, I find it's nothing like I had expected, very unsatisfactory. But if I use the variation of the index as modeled by the new software, I can design and get a result which is very similar to my design goals. So now the issue is to extract the N and K values from our spectrophotometric curves so that we can use this model for practical design. So it turns out we'll do almost all of our measurements at near normal incidence, so we don't run into peculiarities at angles any more than we have to. So I need films which have some transmission. It doesn't necessarily have to have much, but some transmission at all the wavelengths. So I'll run that. I'll run the reflectance in the normal forward direction, and then I'll turn the sample around at near normal incidence and remember it measure its reflectance from the backside. So I get 3 different spectral curves from which to derive 3 different solutions, the thickness and the N and the K at each wavelength. Now, GILLIOT published a paper in a recent decade saying if I take a specific thickness that I estimate bar coating to be, and I generate a line like this %T line, which happens to be straight, of the values in N and K, as would generate the particular thickness that agrees with the transmission curve. And then I use the forward reflection and similarly generate a GILLIOT table where I get the reflection as a function of N and K, and those overlap at 2 different points. So there are solutions at 2 different points, like the solution to the square root has 2 values. And then I use my third spectral curve to plot that. And if all of these intersect at the same 2 points, then I've got a solution that has the correct thickness. If the thickness is incorrect, I'll get either, in this case, too thick at the bottom or too thin at the top, and the middle one is just right. So for all 3 curves to overlap, I have to be using the correct thickness to generate my table. So having found the correct thickness and the N and K value for the 2 different solutions at any particular wavelength, then I've got the kind of data I want. But it turns out, of course, that there's 2 solutions, a right and a left, and this shows the plot of the N value for the right and the left and the K value for the right and the left. But I now have to find out which one is the realistic solution. And here's a plot of the spectral fits for the left solution, and you can see the black line is the fit curves, and the colored lines are the spectral data that I measured. So these are almost perfect fits for the left, and here's for the right, and they look the same. So we got to figure out which one is which. Well, if I take a 4th spectral curve at an angle, like 45 degrees or 70 degrees or something like that, in P polarization is the best, then I'll find which one of these seems to agree. So here the agreement at the right-hand side of this curve is virtually perfect. It starts to depart at the left-hand side, and that's probably some various problem, but it's definitely not the top curve that is of that nature, it's the bottom one. So we have a good solution. So in conclusion, the procedures for determining the N and K and effective film thickness of a sample which has significant absorption but some transmission have been given. And the spectra used are %T, R forward, and R reverse. The 4 spectrum is employed to determine the right or left, which one is the correct solution. And these could be approximately 45 or 70 or something in that range. So the solutions found are more than adequate to provide the production results which agree with the design results, which was our goal. Thank you for your attention.